on Nobel Prize receiving topics 2020 এর আজকের দ্বিতীয় পর্ব। তো আজকে আমাদের আলোচনার বিষয় হচ্ছে ফিজিক্সের নোবেলপ্রাপ্ত বিষয় দ্য ডিসকভারি দ্যাট ব্ল্যাক হোল ফর্মেশন ইজ আ রোবাস্ট প্রেডিকশন অফ জেনারেল থিওরি অফ রিলেটিভিটি। তার আগে কিছু কথা বলে নিই। 2020-এ ফিজিক্স অ্যাকচুয়ালি নোবেল পান হচ্ছে তিনজন। লাইক ওয়ান হাফ ইজ জয়েন্টলি অ্যাওয়ার্ডেড টু রাইনহার্ড গেনজেল অ্যান্ড অ্যান্ড্রিয়া ঘেজ ফর দ্য ডিসকভারি অফ সুপারমেসিভ কম্প্যাক্ট অবজেক্ট at the center of our galaxy. And the other half is awarded to Roger Penrose for the discovery that black hole formation is a robust prediction of general theory of relativity. যেটি আজকে আমাদের আলোচনার বিষয়, এবং এই বিষয়ে আমাদের সাথে কথা বলার জন্য উপস্থিত আছেন ডক্টর নাবিল ইকবাল, অ্যাসোসিয়েট প্রফেসর থিওরিটিক্যাল পার্টিকেল ফিজিক্স, ডিপার্টমেন্ট অফ ম্যাথমেটিক্যাল সায়েন্সেস, দরহাম ইউনিভার্সিটি। তো নাবিল ভাই সম্পর্কে আসলে কিছু কথা না বললেই নয়। ডক্টর নাবিল ইকবাল পদার্থবিজ্ঞানে নিবেদিত একজন ব্যক্তি। তিনি কর্নেল ইউনিভার্সিটি থেকে ফিজিক্সে এবং ম্যাথমেটিক্সে বিএসসি কমপ্লিট করেন। এরপরে এমআইটি থেকে পিএইচডি সম্পূর্ণ করে পোস্ট ডক্টরাল স্কলার হিসেবে ছিলেন ক্যাভলি ইনস্টিটিউট ফর থিওরিটিক্যাল ফিজিক্স এবং ইউনিভার্সিটি অফ আমস্টারডাম। তিনি স্ট্রিং থিওরি, কোয়ান্টাম ফিল্ড থিওরি ও মহাকর্ষ লাইক গ্র্যাভিটি বিশেষ লাইক ভেরি ইন্টারেস্টেড অ্যান্ড কোথায় আর কি রিসার্চিং এ যুক্ত আছেন, এবং সহজবোধ্য স্বাভাবিক ভাষায় পদার্থবিজ্ঞানকে উপস্থাপন করার জন্য বেশ সুপরিচিত। তো ওনার গবেষণা সম্পর্কে বিস্তারিত জানতে আপনারা ওনার ওয়েবসাইটটা ঘুরে আসতে পারেন। আর বেশি কথা বাড়াচ্ছি না, আমরা সরাসরি চলে যাচ্ছি নাবিল ভাইয়ের কাছ থেকে। নাবিল ভাই।
Excellent. Thank you. And okay, so I'm going to get started. So thank you very much for the invitation to talk here. I'm going to apologize. I'll be speaking mostly in English, just because I'm much more comfortable talking about physics in English. So I'm going to talk mostly in English. So let me apologize for that from the outset. Okay. So let me see. I think my slides are not visible. Could you put my slides on the screen? There we go. Okay, excellent. So I'm going to tell you about black hole formation and the 2020 Nobel Prize in Physics. Okay. So as Amina just told us, let's just talk a bit more about what the Nobel Prize was. So as she mentioned to us just now, the 2020 Nobel Prize in Physics was given to 3 different people. One half of it was given to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. The other half was given to Richard Genzel and Andrea Hess for the discovery of a supermassive compact object at the center of our galaxy. So I'm going to tell you mostly about what Roger Penrose did. But you see, if we look at this thing, it's a little bit complicated, right? What does this award actually mean? It's telling us that something is a prediction of the general theory of relativity, and it talks about black holes. I want to explain to you what this prize was actually given for. And to do that, I have to teach you a little bit about the general theory of relativity first. So I'm going to begin by trying to explain to you a little bit of the flavor of what the general theory of relativity is, and then I'll tell you what it was that Roger Penrose actually got the Nobel Prize for. And along the way, we'll learn a little bit about what the other 2 did as well. Okay, so let's get started. So the goal of today is to understand black holes. Okay. I think all of you Sorry?
I would like to interrupt a bit. আমাদের ভিউয়ার্সদের উদ্দেশ্যে বলতে চাই, আপনাদের যদি কোনো কোশ্চেন থাকে সো প্লিজ আপনারা কমেন্ট করতে পারেন। এট দ্য এন্ড অফ দ্য সেশন আমরা সেগুলা আনসার করার করব। ওকে, থ্যাংক ইউ ভাই, কন্টিনিউ।
Excellent. Very good. So we want to understand black holes. Now, to understand black holes, we first have to understand gravity. Okay? And to understand gravity, we actually also have to understand space and time. So let's begin by trying to understand what space and time actually are. So first of all, how many dimensions are there? Well, we know that there are 3 spatial dimensions, right? So for example, if I'm standing here or sitting here, I can move forward, to the left, to the right, forward, back, or up and down. And those are the 3 spatial dimensions. There's another dimension as well, and that's the dimension of time. Okay? So as we move through the universe, we move through space and time. So there are 3 spatial dimensions and 1 time dimension. I think everyone knows this. So what I want to encourage you to think about is that time is a dimension too. But there's something a little bit different about it. Okay? So what is different about time? The difference is that you can choose whether or not you want to move through space. Okay? So for example, I can choose to just sit here, or I can choose to move my head around like this, or move my head back and forward like this. This is a choice. I can decide whether or not to do it. But no matter what, you always move through time. You have no choice. As you exist, time will continue to pass for you, and you always move forward in time. In fact, we can draw a picture of this. Let's do that now. So for example, if I'm sitting here and I'm not moving in space, I continue to move through time. Okay, so this is a picture of me moving through space and time. Now, suppose I start to move to the right. Okay, so normally I lecture on a blackboard, then I can actually stand up and run to the right. So imagine that I'm moving to the right. Okay, what does that look like? Because I'm moving to the right, as time goes by, my position shifts more and more. Okay, that's why this line is now slanted. Now, suppose I go to the right faster. Okay, so I start running to the right. I can go faster, then the line will tilt. If I keep going faster still, the line will tilt more and more and more. And it'll keep tilting as I move faster and faster to the right. But at some point, it has to stop. It can't go arbitrarily fast. And why is that? Well, I think everyone knows that you can't move faster than the speed of light. That means that there's no way for this line illustrating my motion to move more down than this yellow line right here. Okay? But this yellow line indicates the speed of light. Anything else is possible though. Okay? You can have any sort of complicated motion that you like, and it'll look something like this, but it can't move outside of this line. Okay. So now let's keep going. The set of points in space-time where you can go is called the light cone. Okay? So by light cone, what I mean is that you have two light rays coming out from here and here. And you can move anywhere you like in space and time, provided you don't go outside of this area here. Okay? Because if I was going to go outside of this line, I'd have to be moving faster than light that way. And if I was going to go outside this line, I'd have to go faster than light this way. So the set of points in space-time where you can go is called the light cone. Okay, it's everything in here. And why is it called the light cone? Well, over here, I've only drawn one spatial dimension, but as you know, we have 3 spatial dimensions. So actually, if I was to draw 2 spatial dimensions, it would look a bit more like this. Okay? Where over here, you can move anywhere you like inside of this cone, anywhere in the future. And similarly, you can draw a picture in the past, and you can move anywhere you like here in the past. Okay? Okay. So let's keep going. Now let me talk a little bit about sending messages. Here's a little cartoon picture of me. It's a little bit old, this cartoon. I don't quite look like this anymore. But here's an astronaut. Okay? So suppose we have an astronaut moving in space and time, and they want to communicate with me. When can they do it? So if my astronaut is sitting right here, she can only communicate with me when I am inside her light cone. Okay? So if I'm over here, she can send me a message, or she can wait, or she can just walk up to me and talk to me, and that's okay. But if I'm over here, then she can't. There's no way for her to communicate with me, because to communicate with me, the message that goes to me has to go faster than the speed of light. Okay? So these are some very basic ideas, but let me just emphasize that they'll be important in what we talk about next when we get to actual black holes. All right? Okay. So now let's keep going a little bit. Now, we just talked about space and time, so now let's change gears a little bit and talk about gravity. So what is gravity? Gravity, as everyone knows, makes things fall down, right? You know, if you have something and you let it go, it'll fall down because of gravity. So that's basically true. But to talk about black holes, we're going to need to develop a better understanding of what gravity actually is. So to do that, I want to develop this with an analogy. So what I want to do is first talk about the world. Okay, I'm going to discuss the world briefly. So what do I mean when I say the world? So first of all, the world is curved, right? you know that the surface of the Earth is curved. Okay. Now, suppose you didn't know that and you wanted to prove this to your friend. Suppose you have a friend who does not believe that the world is curved. Okay. You have to prove it to them. How do you do that? How do you prove to them that the world is curved? Well, there are various ways to do this, right? So for example, one thing you could do is you could just tell your friend, okay, I want you to start going in one direction. And if you keep going around all the way and you come back, then eventually you'll come back to the same point where you started. And that's one way to tell that the world is curved. Okay, that's fine. That's one way to do it. But that will take a very long time, right? It'll take a very long time to go all the way around the world. Is there an easier way to do this? And there sort of is. Suppose you start at one point on the surface of the Earth and you try to go in a straight line. Okay? In other words, if you start here, take this point here in the Atlantic Ocean, and suppose you take two ships, okay? And you take two ships and you start out with a small angle between yourselves and you start out going in a straight line outwards. Okay? Okay, so what happens then? Now, if you think about the surface of the Earth, it's curved. So if you start at one point and you start going outwards, then you'll go out and eventually you'll turn around and come back and you'll eventually meet each other again, right? On the surface of the Earth. Even if you try to go in completely a straight line, because the Earth is curved, you will eventually come back and meet yourself again, okay? It'll happen quite far away, but it will happen always. So even straight lines meet up again. And this happens because the surface of the world is curved, okay? Because the surface of the world is curved, two lines that are eventually diverging will eventually come and meet themselves once again. Now, I want to talk about something very different. Let me imagine that I'm sitting here, okay, at this point in my chair. And as I've already shown you, if I sit here at this point in my chair, then my trajectory through space and time is a straight line that moves upwards. Okay, that's it. But now, suppose I take this object and I throw it up into the air. Okay, so I'm throwing it into the air like this. Okay. Let me do that again. I'm throwing it like this. So it goes up and then it comes back to me. What does that trajectory look like? So for example, if this is me, okay, then if I throw this green object into the air, then it will go out from me and then eventually it will come and fall back towards me again. Okay. You notice a resemblance. This picture looks exactly the same as this picture here. Well, okay, almost the same as this picture here. So what does this mean? In this case, we had to try to move in a straight line, and we saw that the straight lines met each other again. And that meant the surface of the Earth is curved. Over here, I took two things and tried to move them in a particular way in space and time. And we saw that they came back together again because of gravity. So what does that actually mean? In this case, it meant that the surface of the Earth was curved. Here, it means that space and time are curved. Okay? And this is one sort of very simple way to see that the thing that we normally call gravity is actually the curvature of space and time. Okay? And this is basically one of the many reasons why Einstein is so famous. He showed all of us that space and time are curved, and that's what gravity means. And you can see the curvature of space and time anytime you see something curving because it's falling in space. Okay. So that's the first thing I wanted to emphasize to everyone. The force that we call gravity is actually the curvature of space and time. And this is this field which is called general relativity. Okay. In the Nobel Prize statement, we saw that general relativity was mentioned. This study, the study of how the curvature of space and time affects things, is called general relativity. Okay. So I want to tell you a few details now about how general relativity actually works. And the truth is, this is actually a very technical and mathematical subject, But the rough idea you can understand, and to understand the details, you have to learn a lot more mathematics. So the idea is basically the following. Everything that we have, people, flying balls, light rays, and so on and so forth, everything wants to move in a straight line, but it can't because gravity sort of curves space and time and makes things move in a curvy way. Just like you can't really move in a completely straight line if you're on the surface of the Earth, for the same reason, you can't really move in a straight line in the presence of gravity. And that's basically why anything that's falling looks like it's curving. And you can see this curvature around you all the time. If you think about falling objects, they tend to follow curved paths. That curvature is really a direct manifestation of the curvature of space and time around the Earth. Another important point is that size matters. So what do I mean by that? Imagine you have some very heavy object, like the sun or the Earth or something like that, sitting in space-time. It'll curve space-time in a particular way, kind of like this. It turns out the more the mass of the object, the more the curvature of the space and time around it. So what that means is that paths around it are more curved, and this looks like they're attracted to it more strongly. Okay? This means that if you get closer to a massive object, you will feel the force of gravity on that object more strongly. Furthermore, the closer you are to it, the stronger the attraction. And those of you who have studied physics will know that this is what we normally think of as the strength of gravity. In particular, there's an inverse square law in Newton's laws. You can understand that that tells you that gravity gets stronger the closer you get to an object. The way to see that here is to just see that the curvature of the thing is stronger when you're closer to the object. Now, something very weird happens if you compress a lot of mass into a very small region. Okay, I think everyone knows what this weird thing is. This is a black hole. So a black hole is a region of space that is so curved, where you have so much mass in such a small region that not even light can escape from it. Because not even light can escape from it, it looks black because it doesn't create any light. This happens whenever you have enough mass in a small enough region. If you take some large object and compress it very, very small, then it can form a black hole. Okay? So space is so curved that not even light can escape. So what should you do if you see a black hole? Well, really the point is you should stay away from it. Every black hole has a surface surrounding it, which is called the event horizon. Now, the event horizon is a line that surrounds the black hole. It's a sphere. And if you cross the event horizon, then you can't escape from the black hole again. In fact, from inside the event horizon, nothing can come out, not even light. And because nothing can move faster than the speed of light, that means that really there's no hope at all. Nothing can come out, no space or anything. Okay. So let me now tell you a little bit more about how black holes work. So where do black holes come from? So black holes actually come from stars. So how does this work? If you think about a star is basically a controlled nuclear bomb. Okay? So what do I mean by that? There are lots of complicated nuclear reactions that take place inside of a star, and they try to make the star explode. Okay? The star is trying to explode just like nuclear bombs explode, but in addition to the outwards force coming from the explosion in the star's core, there's also gravity pulling inwards on the star, and there's a balance between those two forces, between gravity trying to pull in on the star and the explosive force pushing it outwards. So that's a balance, and that's why stars exist with a certain size. It's because these two forces are in balance, and that's why our sun exists, okay? These two things balance each other. Now, having said that, you might be a little bit worried, because what happens if the star runs out of fuel? And after all, we have a star here, and it's exploding, but at some point it'll run out of fuel, and then there'll be nothing to stop gravity from pulling in on it. So you might wonder, what happens when it runs out of fuel? Will it collapse into a black hole? So this is a possibility. Once it runs out of fuel, gravity will pull it in, and it could become a black hole, but it's a little bit confusing to understand whether or not it actually does. So let me tell you about that a little bit. So really what we're asking is, do black holes really exist? For many years, no one was really sure if a black hole would exist in real life. So let me explain to you this problem. Imagine you start with a perfectly spherical star and you let it collapse. Okay. It'll begin to collapse. If it's perfectly spherical, then every point on the star will move inwards at precisely the same rate, and the whole thing will eventually collapse down to one very, very tight point. That little point is called the singularity, okay? And it happens at the precise center of the star. And it's sort of easy to understand if your star is completely spherical, that is definitely what will happen, okay? Okay, but you see, in real life, stars are not completely spherical. They have little bumps and little wiggles. I mean, you can see them here. Here's our sun. There's a little bump here, a little wiggle here, and so on. And if you think about it, it's not completely clear what happens if a real star starts to collapse. Because after all, they aren't perfectly spherical. Okay? So what might happen is, you see, this little bit of the star might fall faster than this bit, and this bit might fall faster than that bit. And maybe all the different bits and pieces of the star will miss each other as they fall in. Okay? If they miss each other, then maybe they'll all fly out again. They'll just miss each other and keep flying out, and you won't have a black hole. Okay? On the other hand, maybe the attraction will be strong enough that they will pull in together and form a black hole. And you see, for many years, for about 50 years after Einstein came up with his theory of general relativity, of gravity, people were not sure what would happen, whether or not you could ever get a black hole in real life from the collapse of an actual real star. Einstein himself was very skeptical about this. He used to think it was very unlikely that you could actually get a black hole in real life. So even though his theory predicted, theoretically, black holes, he did not expect them to exist in real life. Okay, so now we're ready to come back to our friend Roger Penrose. Roger Penrose is a mathematician who was in London at the time, and he solved this problem. Okay, in a paper which is actually very short. So while I was preparing for this talk, I read this paper from the original, from the very first time. It's only 3 pages long. And in an absolutely beautiful paper, he proved that actually under very general conditions, if you have inwards collapsing matter, which is collapsing inwards fast enough in a way that he made very precise, this inwards collapsing matter will in fact form a black hole in general, okay? So what that means is that if you have a bunch of stuff and you let it collapse, it will probably form a black hole. And that means black holes can form in real life. And this is called what he called, or rather this is now called a singularity theorem. Because what it tells you is that at some point, if you have collapsing matter, it will eventually collapse into a tight, very tightly curved point, which we call a singularity. So this is a beautiful piece of completely theoretical mathematics, okay? He studied the equations of Einstein's theory of general relativity, and he showed theoretically that black holes will generically form. Okay. And of course, as we know, for that, he was given the Nobel Prize in 2020, last year. Okay. Okay, so that's why he won the prize. But why is this important? So what does this actually mean? What this really means is that space should actually be full of black holes. Okay? Because they can form generically, we really expect that in the sky there should be many, many black holes. In fact, in recent years, we have found spectacular experimental verification of this fact. So let me now tell you a little bit about recent experiments that have told us many beautiful things about black holes. In fact, the black hole in the center of our galaxy, Sagittarius A star, contains a huge, the center of our galaxy contains a huge black hole. In fact, the other half of the 2020 Nobel Prize was given to 2 professors, Andrea Kaz and Richard Genzel, who took very detailed measurements of this black hole in the center of the galaxy. And they are the other two winners of the Nobel Prize in 2020. So here's a picture of that black hole. You can see this bright light in it. The light comes from the fact that hot gases are falling into the black hole, and therefore those emit light. And this black hole in the center of our galaxy has a mass that is 4 million times that of our sun. There's an animation that Andrea Ghez' lab made that I want to show you. Let me see if I can succeed in showing you this animation. One second. Okay, so I believe you can all see this now. And so this is an animation, which is basically the work for which Andrea Ghez' lab won the Nobel Prize. And so you can see right here, this star is the black hole in the center of the galaxy. And all of these other things are other stars that are orbiting that black hole. So you can see that they move and they're all curved towards the black hole in a particular way. By following the motion of each of these stars, we can really learn a lot about the mass of the black hole, how the black hole is rotating, and so on and so forth. We can learn all of those things from looking at the motion of how these stars go. And this is an amazing piece of observational physics. And this is why Andrea Ghez and Richard Genzel won the other half of the Nobel Prize. Okay, so let me now go back to my slides. Okay. I just want to say a few more very quick things. Another way in which we know that black holes actually exist in real life is through the existence of gravitational waves. So what are gravitational waves? Sometimes you can have two black holes which collide and form a bigger black hole. This is an extremely violent event. Okay? When that happens, it creates a huge disturbance, and it creates ripples in space and time. Okay? And those ripples, those waves, are just literally waves in the fabric of space and time itself, and they go out from the black hole in all directions. And if those ripples pass through you, what really means is your size will change ever so slightly. As the gravitational wave goes through you, you will change in size, and in fact, you will become twisted like this. You'll first become elongated like this, and then squashed like this. In fact, we can detect these gravitational waves on Earth. There are very careful observatories, which are basically very, very carefully built rulers. And the lengths of those rulers change as the gravitational wave passes through the Earth. Okay. And the very first one that we detected hit Earth on September 24th, 2015. Here's a picture of what that looked like. So what happened was we had two black holes, they collided and hit each other. And in the process, they keep creating gravitational waves. There are actually two different lines here. There's the prediction in red from Einstein's theory of general relativity, and in gray is the experimental results. You can see they exactly agree, and this is yet more evidence that general relativity is the correct description of gravitational waves. Okay. And as I mentioned earlier, the very first one that we detected hit Earth on September 14, 2015, and they reported it a couple of months later. And in fact, the Nobel Prize in 2017 was given for the discovery of these gravitational waves. Okay, so these are some experimental consequences of black holes. But now you might have one more question, which is, I have told you that you should not go near a black hole, but suppose you do anyway. Okay, suppose you go into a black hole and fall inside of a black hole. What happens? What is going on inside a black hole? And so for the last 5 or 6 minutes or so, I want to tell you what's happening inside the black hole. So first of all, this is a picture of the space and the time outside or around a black hole. Okay? Let me explain this picture a little bit. This picture is called a Penrose diagram. Okay? And this is yet another thing which the same person, Roger Penrose, invented. He told us how to draw these pictures. And so the key point about this picture is that time runs upwards. So time goes this way. If you're moving forward in time, you'll move like this. And space is outwards here. And light rays move along 45-degree lines in this picture. Just like when I earlier showed you a picture of space and time, it's the same kind of picture. Okay? So this is a picture of a black hole. Let's try to understand why. So suppose I'm over here and my astronaut friend is here. Now, I can communicate with my astronaut friend. I can send her a light ray. Okay, I can reach her. But let's think about what happens if I fall inside the black hole, which means that I cross this dashed line over here. Suppose I enter the interior over here. Now, because the light rays move on 45-degree lines, once I'm inside, there is no way for a light ray from me to reach the outside of the black hole. Okay? The light ray simply cannot go there because the light rays always travel along 45-degree lines. But because I'm always supposed to move inside of these two light rays, I can only move like this, which means I can never escape from the black hole either. So once I cross this line, I am stuck moving inside here. I can never escape out here. Okay? The singularity is this red line here. Okay? It is very, very dangerous. If you hit this thing, then you will die. Because space and time there is very, very, very curved. Okay? So space and time there are very, very messed up. And if you hit this singularity, then you'll die. And you can see from this that I drew the picture earlier to make it look like the singularity was a point in space. Actually, the singularity isn't a point in space. It's a moment in time. Okay? Because time goes this way. You can imagine you have 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock. Just like 5 o'clock is a moment in time, the singularity inside of the black hole is a moment in time. And what that means is just if you continue to exist, you will eventually hit that singularity. And you see, that's why it's so scary. Because if I ever fall into a black hole, not only can I not escape from the black hole, I also have no choice, but eventually I will hit the singularity and die. But no one from the outside will ever be able to see this happen. So it's also a very lonely death. Okay? Okay, so let me summarize. Gravity is the curvature of space and time. Black holes, here's a picture of one, are objects that are so massive that not even light can escape from them. Roger Penrose predicted that black holes should generically form from any sort of collapsing matter, and it was for that discovery that he was given the Nobel Prize. And finally, experiments continue to tell us more and more about black holes every day. Okay, thank you for listening.
Thank you, Mara. That was অসংখ্য ধন্যবাদ আসলে এত সুন্দর করে আমাদেরকে এই ব্ল্যাক হোল সম্পর্কে করার জন্য। I had one question আর কি, যে black hole can be formed like by collapsing matters. So black hole existence কিভাবে করে? Like suppose there exists a black hole. How do we predict that there exists a black hole? Existence কিভাবে?
Good, very good. So there's many ways to do this. So the question was, how can we really tell that a black hole really exists? That's the question. Is that right? So there are two ways to do this. You can do it theoretically, the way that Roger Penrose did. He proved that that the solutions to Einstein's equations generically have something, so that if you fall into it, you can never escape from it. But nowadays, we don't have to do that. We can do things like looking at the experiments. Like, for example, I showed you earlier, there's this animation of the stars orbiting the black hole. If you look carefully at how the stars move around the black hole, then you can tell that their motion is exactly in agreement with what would happen if a black hole really existed. You can look at the pattern of the light that comes off from these things falling into the black hole. They give off light. So here's a picture of it, and here's another picture of it. And the pattern of the light coming off, it's really very characteristic of the way that the black hole, you can sort of directly tell that the black hole is there by looking at the way that the light comes off from the stuff falling into it. So basically, it's a little bit indirect, but the predictions of Einstein's theory tell us how things should behave near the black hole, and from that we can tell the black hole really exists. Okay. Now you see, you can't see the stuff inside the black hole itself because the black hole is black, right? Nothing from inside can come out again. So the best you can do is look at stuff that's about to fall in, and then from that you can figure out that a black hole must be there. Okay, that's the idea.
Like, is there anything, কোনো স্টার কি কখনো লাইক ব্ল্যাক হোলে ইয়ে করছে, এরকম কোনো এক্সপেরিমেন্ট করা হয়েছে, লাইক স্টার রিভলভিং অ্যারাউন্ড দ্য ব্ল্যাক হোল এন্ড দেন gets inside the black hole?
Well, experiment, I mean, it is a good party. Of course, we just have to hope that this happens in space. But indeed, so I showed you a picture right here of two black holes orbiting each other, and then they collapsed and formed a disaster. Okay, that happened here. This is a thing that happened in 2015. But since then, there have been many, many more of them. And for example, one thing that happened was that you can have a neutron star here and a black hole here, and eventually the neutron star will orbit the black hole and then fall into it. Okay? And so this happened more recently, and there's a plot just like this of that process happening, for example. Okay? So yeah, that kind of thing does happen, and it'll happen more and more as time goes on. So what happens is, in the sky, these things are happening all the time, and we just kind of sit here and listen. We hope that one of them happens, and we can detect the gravitational waves coming from that. Okay. Excellent question.
Like, can we predict any star falling? Like, আমরা কি predict করতে পারবো যে এই স্টারটা দের এত বছর পরে, like other astronomical things predict করতে পারবো কিনা?
I think that's a good question. I'm not actually an expert on this. I think this might be a little bit difficult to do because these things happen on very long time scales typically. You know, the final process is very short. So the final process happens in 4 or 5 seconds, like right over here. You can see this in seconds. But the whole thing can take thousands of years to spiral towards that and eventually fall in. I think that makes it very hard to do this prediction. But the truth is, I'm not really an expert on that side of it. So I don't want to give a very clean answer to that. Yeah, it's a good question. So I'm sure they're trying to do such things now, but I don't think it's very easy. So.
Okay. I think that's all for today. ভাইকে অসংখ্য ধন্যবাদ আমাদের সাথে এই সেশনে জয়েন করার জন্য। আমরা আসলে এই যে ফিজিক্সের নোবেল প্রাপ্ত বিষয়ে আজকে জানতে পারলাম এবং খুব সুন্দরভাবে এই জেনারিক ওয়ে এক্স্যাক্টলি। আশা করি আমাদের ভিউয়ার্সে অনেক হয়েছে। ভাইকে আবারও ধন্যবাদ জানাবো, অ্যান্ড সেই সাথে সবাই ভালো থাকবেন। এই বলে আজকে আমাদের এই ওয়েবিনার সেশনটা আমি এখানে শেষ করে দিতে যাচ্ছি। ধন্যবাদ সবাইকে।